Okay, we will continue on our lectures. Okay, everybody ready, right? Okay, so I start recording our lectures. Okay, so let's see. Oh, cannot move my slide again. Okay, oh, stop sharing and then share again. Okay, so last time we talked about the component and some example of the spark ignition engine, right? Okay, we already finished on that on the SI engines. Okay, so we will continue today to finish our lecture number 1, and then we will also cover lecture number 2. Okay, for some part of lecture number 2. Okay, so let's talk about the compression ignition engine operations. Okay, for the compression ignition engines, normally we call it in short CI engine, right? C stand for compressions, I stand for ignitions, right? And it's usually called the diesel engines, right? I put in the bracket at least in European country, right? Because some country, they think that Dr. Durab diesel is not the first one who invent the diesel engine. So they prefer to call it in another name. Okay. But in Thailand, we call it diesel engine. Okay. For the diesel engine, right, the main characteristic of the diesel engine is that the fuel is injected with a very high pressures. Not only high pressures, but is injected directly into the combustion chamber just before the piston move up to the top dead center. Okay, so this is the main characteristic. So you should see that if you are in the combustion chamber, right, and if you are not in the combustion chamber, if you are a fuel, then when you are injected into the combustion chamber. What you see inside the combustion chamber is the air, right? And that air already have high pressures and also high temperatures, right? So there is no questions why this fuel have to be injected in a very high pressure, because inside the combustion chamber, they already have the air with high pressure already, right? So the fuel pressure have to be higher than those of the air, okay, or that of the air. Okay, then the fuel will ignite on the condition that the temperature created by the compressions, right? Or in other words, the air temperatures is high enough, right, for self ignitions or for auto ignitions. And then when the fuel ignites, right, you can see the burning spray of the fuel happen, right? That means the fuel, right, the burning frame start to travel, or the flame front or the frame start to travel or propagate throughout the combustion chamber. This is what you see, right? And then the combustion that happen, right, can be controlled by the way you mix the air with the fuel vapor, right? This is how we can control the combustion, right? How the combustion can be controlled. Okay. Again, right, in the previous lectures, we already see this kind of diagrams, right? That is for the 4-stroke SI engines. Okay. Now this one I show you for the naturally aspirated 2-stroke CI engine. Right? So that means it is a 2-stroke CI engine that draw the air by itself, right? Purely by itself. No other device help them to draw the air into the combustion chamber or into the cylinder. Okay, I show you this 4 diagram. Right? There are 4 diagrams altogether. The first one, right, give us the ratio of the cylinder volume at any crank angle positions to the clearance volume. Right? So it's V over VC. Right? So you can see it's go up and down, right, like this, and it will give you the maximum value of the ratio when the piston is at the top dead centers, right? And along the way, you will see the positions of the crank angle where the inlet valve closes and the inlet, the exhaust valve opens. Okay. The second one show you the mass of the fuel injected or the rate of the fuel injected. Right? You can see that the fuel start to be injected just a little bit before the piston move up to the top dead center, right? Okay, and then it keep injected as long as the piston still moving up until just little behind after the piston reach the top dead center and start to going down. Then we will end the injections of the fuel. Right? So EOI, end of injections. SOI, start of injections. Right? So we have a very short period of time, right, according to this diagram, to inject the fuel into the combustion chamber. Okay. And the third one gives you the sense of how the pressure inside the chamber is distributed, right, according to the motions of the crank angle. Okay, so start from here, right? The piston is keep moving up from the bottom dead center, right, until just far away, right, far away from the bottom dead center. So you can see that the inlet valve is closed. So that means from here to here, there is a gas exchange process happen, right? Because both the inlet valve and the exhaust valve both are open. Right? Then the inlet valve closed, no more gas exchange process or scavenging process happen. Right? Then the piston still could keep moving up, right? Okay, and then up to here, before the piston move up to the top dead center, we have the start of the ignitions, or start of injections here, SOI here, right? But the fuel still not burned yet. Why? Because we see that the pressure is still on track with the motoring curve. I remember about the motoring curve. The motoring curve represents the engine operation if there is no combustion happen, right? So we have we start the injection right here, but there is no burning of the fuel or no combustion happen, right? Because the pressure is still on track, the same track with the motoring curve. Then after that, a little bit after that, then we can see the start of the combustion happen. So that means the fuel start burning, right? Start burning. How do we know that the combustion start here? Because you can see the pressures, right? The pressure here start to deviating, right? Start to deviating from the motoring curve, right? So the pressure go up, right, very rapidly, right? You can see the high slope in the increasing of the pressure here. So that means the combustion still happen as the piston moving up to the top dead center, and then even the piston move down from the top dead center, the pressure still increase because of the combustion that happened. until it reaches maximum pressure here, then it starts to go down, right, along with the piston that moving down. Okay, until down here, right, no more combustions, right? Combustion finish, and then the pressure go down rapidly and then slowly, right, as the piston move down to the bottom dead center. Right. But before the piston move down to the bottom dead center, the exhaust valve open here, right? The exhaust valve open right here. Okay, so this is how the pressure is distributed, and from the pressure distribution, we know what happened, right? We know when the injections happen, we know when the combustion happen, right? We know when the combustion finish. Okay, and the last one tell us about the mass of the fuel burning, right? It's different from the mass of the fuel injections. Okay, see from here, from this diagram, you see we inject the fuel right here, but there is no fuel burning. Right? We have to wait a little bit, right? Then the fuel burn, right? And it will burn rapidly, right? It will burn rapidly, right? So you can see the lines go up very fast, high slope here, right? And then after that, it drop down a little bit before it's go up again, and then going down. Okay, so this tells us that the injection of the fuel doesn't mean that the fuel will burn immediately when we inject the fuel into the cylinders. Okay. So this is what happened for the naturally aspirated two-stroke CI engine. Okay, how about the loop Scarvent two-stroke CI engine? The loop Scarvent, if you remember, for the two-stroke engine, we can have valve, either intake valve, or we can have the port, right, to intake or exhaust the gas inside the chamber. Okay, so I show you here is for the two-stroke CI engine that use the port, right, to exchange or to scavenge the gas that happen inside the cylinder. And the way they use the loop scavenge. Okay, the first one, right, tell us again the ratio of the cylinder volume to the coolant volume, right, is go pretty much the same, right? Nothing changed because it's totally physical, right? It mentioned about the physical of the cylinders, right? Nothing involved with the combustion phenomena. Okay. Okay. Another one is the pressures. Right. So this first diagram show you both the volume, the ratio of the volume, and also how the pressure is distributed, right, along the way that the crank move. Okay. So right here, right, the start of the combustion happened before the top dead centers, right? So again, you see, we know that the combustion happened because the line of the pressure deviate from the motoring line or the motoring curve here. So the pressure go up and reach the maximums, right? Even the maximum point happen, even the piston move down from the top dead center, it not happen, right, at or where the piston is the top dead center. Okay, this is something that you have to remember, right? The maximum pressure happen right after the piston move down from the top dead center. And this is very important because we would like to have the maximum pressure, right, as close as possible to the top dead center, right? If you look at thermodynamics, right, we have the maximum pressure, right, always at the top dead center or where the piston move up to the top of the cylinder. But practically, right, we never get that, but we try to get this maximum pressure as close to the top dead center, right? Because that will give us the best efficiencies, right, of the engines. Okay, so the maximum pressure right here, a little bit after the top dead center, and then it's go down, right, as the piston is moving down, right, until right here where the exhaust port open, right. The scavenging process will not happen. The exhaust port open first, remember, and then after that, then the inlet port open. After that, the inlet port open. These two ports open before the piston move down to the bottom dead center. Okay, and then the piston go up. You see the pressure go down because the port open, right? So inside the cylinder, right, when two port open, there is virtually there is no pressures inside the cylinders. Okay, then after the piston move up from the top dead center, right, the inlet port close, right, the inlet port open after the exhaust port open, but the inlet port will close before the exhaust port close, right? Okay, so the inlet port close, and then after that the exhaust port close. Okay, so the pistons keep moving up, and then the pressure start to rise because now you have a closed volume inside the cylinders, right? Because both ports are closed now. So the pressure start to rise, and then the combustion happen, right? So the pressure deviate from the motoring curve again, and then go up high. Okay, so this is show you how the pressure is distributions inside this loop Scarven to Stokes CI engines. Okay, the second diagram down here show you how the area of the port, no matter it's the exhaust or the intake, open, right, according to the crankshaft motions. Okay, so start from here, right? The exhaust port open. You can see that when the port open, it will gradually open. Right? It will not open sharply like this. It's gradually open until it reached maximum opening here. Right? And it will keep its maximum opening for a period of time. Right? Between the piston move down to the bottom dead center and between the piston move up to the top dead centers. Okay, this is where the port keep their maximum opening here, right? For both the inlet and the intake port. And when the exhaust port open, right? After that, then the inlet port open, and you can see that the inlet port open rapidly or higher, more rapidly than the exhaust port. Right? So it takes just a little bit of time in order for it to have a maximum opening, right? And the maximum opening area of the the inlet port is a little bit higher than the maximum opening of the exhaust port, right? And then it's closed before the exhaust port here. So this is how the port area vary along the way that the piston move. Okay. Below here give you all again the pressure distribution, but it gives you more detail about this pressure distribution area up here, right? So in here, right, since it involved with high pressure and very low pressure, so you cannot clearly see on these portions, right? So they show it right here, right? Only right here. So you can see more clearly how the pressure is distribution over here. Okay. So in this diagram, right, you will see that they have other two pressures, right? This is the inlet pressures. The inlet pressure is the pressure of the charge or the fuel, right, that carry with it, right, to go into the chambers. And this is the exhaust pressure, that is the pressure outside, or the outlet pressures, the pressure outside of the chambers. Okay, these are two reference pressures. Right. One is the pressure that carry with the fluid, the fuel itself. Another one is the outside pressure of the chambers. Right. We show this too because it's important, right? So you can see that from here, the pressure start reducing, right? Because the piston keep moving down, right? And from here, the exhaust port open. So if you know that the outside pressure is this, then you know why the exhaust port have to be open right here. Because at this point, the pressure inside the chamber is still higher than the outside, right? So the exhaust gas inside can easily flow out, right? As along the way that the pressure start to decreasing, right? So the exhaust port open first because of this, okay? And then when it moves down here, right, it's still higher than the pressure outside. Even up here, it's still higher than the pressure outside or close to the pressure outside, right? And then the inlet port open, right? So when the inlet port open, it makes the pressure inside the cylinder to even go down below the exhaust, the outlet pressure here. So you can imagine that during this period of time, from here to here, right, the exhaust gas inside the chamber cannot flow out because the pressure of the exhaust gas is lower than the outlet pressure here, right? Okay, but the pressure of the fuel that injected is higher, right? So from here to here, you can see that if you are in the chamber, you can see that only the fuel is flowing in, right? And because of the fuel, right, when it flows, it not only flow with its mass, but it also flow with the pressure. So that will help the pressure inside the cylinder, right, to go up, right? And who get the benefit? The exhaust gas, right? So the pressure inside the cylinder start to go up and then higher than the exhaust gas, the outlet pressure here. So that means what? The exhaust gas inside the chamber start to fall out again. Okay. So this is the benefit of the pressure from the fuel that we inject into the cylinder. So it can help the exhaust gas, right, to be able to fall out again because the pressure inside the cylinder start to go higher than the outlet pressures, right? So it's go up until the inlet port close, right? The inlet port close. No more uh, helpful force for the exhaust, right, pressures. So the pressure inside the cylinder start to go down, right? And then just a little bit before, right, it reach the exhaust, the outlet pressure right here, then the exhaust port close. Right? No more gas exchange, no more gas exhaust gas to fall out. Okay, so and then the pressure keep going up, right? Because the piston move up to the top dead center and both ports are closed. Right? We have a closed volume. Okay, so this is how the gas exchange process happen, right? It depends on the outlet pressures and depend on the inlet pressure of the fuel that is injected into the cylinders, right? And it show you right here on this third diagram. Okay. Okay, so let's take a look on how the mixture can be generated for the CI engine. Okay. Any questions so far? Any questions so far? No? Hello? Mhm. Okay, if there is no questions, then we will go on for the mixture generation method in the CI engines. Right? The first method is the old one. Okay, it's called the pre-chamber injections or the indirect injections. Right? This injection method normally used for the small high-speed engines. And the injector that they use is called a simple tappet injector. Right? This is how we call it a tappet injector. Right? You can see that here. Right? It tap a little bit, right, down here. Right? Not go for the straight line, is an inclined line here over here. Okay. And the injection pressures for this type of mixture generation is kind of low, right? And even it's low, when you look at the blanket here, it's not more than 300 bar. Okay. This is considered to be low. Okay. Okay. Not more than 300 bar. Okay. Right. And that means what? If the injection pressure is low and you want the engine to work efficiently, that means this engine requires a high compression ratio, right, to effectively work for us, right, because they cannot rely on the fuel injection pressure, right. They need to have a high compression ratio here, okay. And it also provides, right, for this method, it creates a high thermal load, right, because if you look at this is a small pre-chamber here. That's the reason why they call it a pre-chamber injections, right? Because for this method, we need to have a small pre-chamber right here. So that means what? The combustion happen right here. And since the chamber is small, so you can expect that this chamber will what? Experience a high thermal load here. Okay. And because of this engine will give us a low efficiency, and you can see it in the old type of the car, the diesel car, right? Old type, right? With I don't think that they know nowadays they still exist. Okay. Okay. So the second method come in, right? And this is more widely used, and presently is still used. Okay. We call it the direct injections. Right? For this method of mixture generations, right, we have more than one injectors, right, per chambers, okay? And for that injector, we do not have only one hole. We have a multi-hole, that is more than one hole injectors, right? And this injector, right, will inject the fuel at a very high pressures. That means what? More than 300 bar, right? More than 300 bar. And this injections method, right? This injection method, right, will not rely only on itself for mixture generations, right? It also rely on the shape of the intake port, right? The port where the fuel entering the chamber. Right? It also rely on the shape of the intake port in order to what? In order to induce the air inside the chamber, right? To swirl, right? So in other words, to give the air a highly turbulent flow, right? So that the fuel can interact with the air efficiently, right? And that will result in the high efficiency of the engines, right? If they use the direct injection method here for their mixture generations. Okay. Another thing is you can see from these pictures, the combustion chamber, right, is in the piston, right? You can see that on the top of the pistons, right, they dig it, right, to be a hole here for some portions, right, in order to create the combustion chamber here, right? So the combustion happen, right, in the piston, okay, not in the cylinder, it's in the piston. So the air, the fuel, everything will fall into this combustion chamber here, okay. And this direct injection method is good for the high-speed engine, good for the high-speed engine, right? And apart from that, right, this injector is normally used in conjunction with the exhaust gas turbocharging, right? Because since the fuel, right, is injected in a high pressures, right? So the air, the amount of air that flow in have to be able to catch up with the fuel, right? In order for the air to be able to catch up with the fuel, we will not rely on the engine itself, right, to draw the air into the cylinder, right? We help them by adding the turbochargers, right, in order for the engine to be able to draw more air into the chambers. Okay. For medium speed engine, right, if you want to use the direct injections, normally they will use only one injector, not more than one, right? For the high speed engine, they use more than one, but for the medium speed CI engine, they will use just only one injectors, right? And for low speed CI engine, right, for low speed, that means they require more torque, right? Now they come back and use several injectors, but typically not more than 2 or 3, right? Not more than 2 or 3. And for low speed CI engine, they also make use of the shape of the intake port in order to induce the highly swirl airflow also, right? And to help the exhaust gas to go out, right, easily, they usually locate the exhaust valve at the middle of the combustion chambers. Okay. This is for the low speed CI engine. Okay. This picture show you the diesel fuel supply systems. Okay. So start from the fuel tank here, right? The fuel is drawn by the supply pump here. Okay, so this is the supply pump where we have this portion to do the plumbing, right? To do the plumbing because the fuel tank is lower than the supply pump here. So we have to do the plumbing in order for the fuel be able to draw by the pump here, or the pump can draw the fuel down here, right? And then it will give the high pressure to the pump, to the fuel. Right? This pump give the high pressure to the fuel, and the fuel will go to the fuel filter, right? To filtering out all the dirty thing in the fuel, and then fall down to the manifold here, right? So the pressure, the fuel already have the high pressure here, and for manifold here, it will fall to the fuel pipe and then to the nozzles and the holder assembly, or we call it the injector in short, in here, where the fuel is injected. Okay, so now how we can control the amount of the fuel, right? because this pump has to be responsible to deliver the amount of the fuel to all the injector, right, that connect to this manifold. So how we can control the amount of the fuel that is injected through each injectors, right? To control, right, you can see that we have this overflow line here for the injectors. That means what? The excess amounts of the fuel that flow into the injector, right? All of the excess amounts of the fuel will flow to this overflow line and then back to the fuel tanks, right? Same as the manifold here, right? That we also have the overflow line here, right? So that the excess fuel will flow down to the fuel tanks. Okay, so this not only control the amount of the fuel that is injected through the injector, but it also ensure that we will have sufficient amount of the fuel all the time for to the nozzles. Okay, so this is the good part. We will not try to directly control the amount of the fuels to the injector. What we do is we indirectly control the amount of the fuel that flow into the injector by using this overflow line here to help us to control the amount of the fuels. Okay. I hear the heat sound. Students should close your microphone, please. Okay, thank you. Okay, so look at the pump. Okay, back to the pump here. So this is the governor part of the pump, right? That control the functions of the pump. So control how the pump working, right? And this give you the power to the pump, right? It's a drive from the engines, which provide also the timing device here, right? The timing device, right, tell us that when the pump should operate and when the pump should stop, right? This is what the timing device do, right? Give us the signal, give the pump the signal that now you have to stop, now you have to stop, okay? And then who make the pump to stop and start? Here, the cut-off lever, right? This will make the pump to start and to stop according to the signal received from here. And if you remember this word, cut off, right, in thermodynamics, right? We use this cut off in here for this lever, right? The reason we use this because if you remember in thermodynamics, when you study the diesel cycle, right, there is one parameter called what? Called a cut-off ratio, right? This tells us that when we stop providing the fuel to the cycle, right? The cut-off ratio gives us the information that when we stop sending the fuel into the cycles. Okay, so they use this word here, the cut-off level here. Okay. Okay, so this is show you in more big picture about the inline fuel injection pump. Okay, we have the deliver valve holder. Right, this is where we connect the fuel pipe to the injectors, the cut-off level here, the governor here, and the timing device here. And this is where the fuel supply to the manifold here. The manifold is inside here, right, in the same body as the pump. And this is the pump itself here. Just a small pump. That's why we call it the inline injection pump. Okay. Okay, and this gives you the detail of how the fuel injection nozzle look like. Okay, there are two types of the nozzles. Right, one we call is the pintle nozzle. When you talk about the pintle nozzle, it's normally one hole nozzles. And then we have the second type, multi-hole nozzles. Right. So these two pictures show you the pintle nozzles, and this one show you the multi-hole nozzles. Right. When you have a multi-hole nozzle, you get the spray of the fuel. That's why you have the spray angle. It's come out because you have several holes on the nozzles. But for pintle nozzle, you don't see the spray angles because there is only one hole. Okay, and the left picture here, right, show you when the pintle nozzle is at close positions, right? So you can see that the nozzle needle is go down here, right? Stop, close this opening, small hole here, right? And you see that this is the inlet port where the fuel is traveling inside the nozzles, right? And this is an angular groove inside the nozzle. Again, this is the passage for the fuel to go around the nozzles. Okay, and the middle picture here, right, when the pintle nozzle is at the open positions, right, the nozzle needle is lifted, right, so the fuel, right, represented by the black color here, right, will flow through this hole, right, into the chambers. Okay, so this is what we call, this area we call a chambers, right, a tiny one, right, a pressure chamber you can call it, right, a tiny chamber here where the fuel is waiting, right, when it flow into the nozzle. Waiting for what? Waiting for being injected. Okay, same as the multi-hole nozzles, right? They have inlet port, they have the angular port, the same, except here, right? Below here, that is different because below here we have several holes here instead of one single hole. Okay. Okay. Now this one give you the whole big pictures of the nozzle holder, right? Previous picture just show us these portions. Okay. This portion already show into detail on these pictures. Okay. But the full nozzle is shown right here, where you see the mechanism like that, open and close the nozzle needle. Okay, the nozzle needle is right here. Right, the nozzle needle is open because of the fuel pressure here. Right, remember the fuel is sending in from time to time. So the pressure occurs from time to time. When the fuel flow in, they have pressure, right? And this pressure will lift up this nozzle needle. Okay. And then when there is no fuel sending in, right, or no more pressure supply to the fuel because the pump stop, right, then the spring over here will force the needle to go down. Okay. And inside the nozzle holder, you see the line of the pressure that flow out to the overflow line. They call it the leak off connection, but it is the overflow line that we mentioned earlier, right? So the excess amount of the fuel, right, will go to this portion or this passage, right, and out here, right, back to the overflow line. Okay, so this is how the needle is open and closed. Open because of the pressure of the fuel here, and closed because of the spring here, right? And top here is how you can adjust the force of the spring here, right? From time to time, when you use the engine for a longer period of time, then you have to do the maintenance, you have to do the injector cleaning, or you have to adjust the injector in order to provide a proper amount of the fuel at the proper time. Then you put your car into the maintenance center, and then the mechanic over there will adjust the speed inside here by using this adjusting screw. Okay, so next let's look at how we can control the fuel delivery. Okay, before that I told you that the needle go up and down, right? Okay, but it not only have a linear motions, it also have rotational motions, right? The rotational motions of the needle, or in here we call it the plunker, right? You can call it needle, you can call it plunker, okay? The rotational motions of the plunker or the needle, right? The nozzle needle, is used for controlling the amount of the fuel delivered, okay? And also the angular groove, in which here we call it the helical groove, right? Is also a helper, right, to control the fuel delivery, right? The reason we have to control the fuel delivery because we have to vary the amount of the fuel according to the loading that happen to the engines. Okay, so linear motions of the plunker is for close and open. The rotational motions of the plunker is used to control the amount of the fuel delivery. Okay, so I give you three groups of the pictures, right, that show you how it can partially deliver the amount of the fuel and how it can provide the maximum delivery of the fuel and for zero delivery of the amount of the fuels. Okay, so first look at for partially delivery. Okay, you see in the plunker, the top of the plunkers, we have the groove. This is a vertical groove. Okay, when the piston is at the bottom dead center or at the end of the nozzle, right, is closed. Right? If it want to be partially opened, right, so it will lift up. Right? It will lift up. Right? Along the way that it lift up, it rotate. Right? It will not let this vertical groove, right, to face directly with the supply port of the fuel. Okay, this will happen when it want to deliver partial amount of the fuel, not full amount of the fuel. This groove, right, will not rotate until it face directly with the fuel delivery port, which is right here. Right? But for maximum delivery, right, it will rotate such that this vertical groove, right, will face directly with the fuel, right, inlet port here to the nozzles. Okay, this can provide the maximum delivery of the fuels. And when it provides zero, right, it go down. Right? No more fuel delivered to the nozzles. Okay, so this is how the fuel is controlled, right? The amount of the fuel is controlled by using the motion of the plunker or the motion of the nozzle needle. Okay. Okay, so let's go to see some example of the diesel engines. This is, I show you the famous diesel engines, right? Its name is Duramax. This is the 4.5 liter V8 Duramax engines. Anyone know that this Duramax is what manufacturer brand who produce this Duramax diesel engines? Any student? Hmm? Hello? Hello? No answers? Hmm? Hello? ไม่ได้ยินเหรอ
General Motor หรือเปล่า
โอ้โหทำไมตอบช้าจัง ตกใจเลยนะเนี่ยนึกว่าให้พูดอยู่คนเดียว โอเค it's not General Motors okay it from Isuzu Duramax right? The king of diesel engine is Isuzu okay not General Motors okay and you know what right? The highest sales of the pickup car is in what country? The highest amount of sale for the pickup car, right, is in what country? Anybody know? The highest amount of pickup car, the sales of the pickup car, in what country? If you don't know, just say no. Okay, so I can give you the answers.
no ครับ
No, okay. In your country, this country, right, have the highest amount sale of the pickup car. Okay. Surprise, surprise. Okay. So this picture gives you the indirect injection diesel engines. Right? How do we know that it's indirect injection diesel engine? Because if you look at here, you see a pre-chamber here. Right? Whenever you see a pre-chamber, it means indirect injection diesel engines. Okay. And this I show you the turbocharged diesel engine. The turbocharged diesel engine. How do we know? Here, this is the turbocharger attached to the engines. Okay. This is how the turbocharger look like. Okay, so now we finish the SI engine and also the CI engine. Okay, let us take an overlook on the overall characteristics of the SI engines. Right? Okay, the working cycle is called the Otto cycle. It uses the gasoline or the high octane fuel. Right? Again, what is the amount of the octane that we use in our country? What is the octane number for the fuel that we use in our country? Anyone know?
80
Huh? 80?
80
80. How do you come up with this idea? 80. 80. You said the octane number of the fuel that used in Thailand is 80, right? How do you come up with this number? Mhm. Have you ever been?
85 and 81
What? You can speak in Thai if you are not as accustomed to the English. That's okay. I just want you to learn. Okay. Don't be obstacle because of the language. Okay. How do you come up with these ideas? That 80 octane number of the fuel in Thailand.
from
How?
the gas station.
From the gas stations. But I about to ask you, have you ever been to the gas station or not? Because in the gas station, you never see the letter 80, right? What you see is what? What is the number you see on the gas stations? On the signage?
85
85. Are you sure 85, that number called 85? I believe that that number
91
91 and 95, right? 91 and 95, right? That number represent the octane numbers. Okay, that number represent the octane number or the gasoline fuels, right? So our country use the fuel with 95 octane numbers or 91 octane numbers. Okay, Then what is about the high octane fuel? When you talk about the high octane fuel or high octane number fuels or fuel with high octane number, it means that fuel have a high cell ignition temperatures. Okay, this is the characteristic of the high octane fuel. So the Otto cycle or the SI engine, they require the fuel that have a high cell ignition temperature, right? And both fuel and air are introduced together as the gas mixture in the intake stove, right? So fuel and air, right? They will introduce into the combustion chamber as a mixtures for the Otto cycles, right? And to create the mixtures, right, we use the carburetor. That's why we talk about the carburations, and later on we talk about the injections. Okay, so here is to provide the mixtures. Okay, and we control the amount of the mixtures in the SI engine by using the throttle valve, right? Or in other words, the butterfly valve, right? They can call it also. This is to control the combustions in the chambers. Okay, for the Otto cycle, you need to have a spark plug. Right? The reason why you need the spark plug for ignition, because the compression ratio for this type of the engine is not that high. Right? You can see the compression ratio is just 8 to 12 or 13. Now I think it's go up to, let's say, 15, but that not still consider high compression ratios, right? So they still need a spark plug here, right? This engine, right, can provide a higher maximum RPM. That means what? You can running this engine at a higher RPM, right? Or the speed of the engine can go higher because this engine is normally have a lower weight, right? It's not a big or bulky type of the engine, right? It also provide the maximum efficiency. Oh no, the maximum efficiency is lower, correct? Okay, the maximum efficiency of this engine is lower, right? Because of what? Because of the compression ratio is low, right? And the last one, engine is lighter according to this. Okay, lower weight here. Okay, so this is the overall characteristic of the SI engines. How about the CI engine? The CI engine. The working cycle is called the diesels, right? And it uses diesels or high cetane fuel, different, huh? For the auto or the gasoline fuel, we use octane, right, to represent the class of the fuel. But for diesel, we use cetane number to represent the class of the fuels, right? So what is the characteristic of cetane, right? We talk about the high cetane fuel. In Thailand, right, at the gas station, you don't see that they put any number of the cetane on their diesel fuel, right? You don't see the numbers. Okay, you only see the octane number. You don't see cetane numbers. Okay, I don't know why, but maybe because we don't have different class of the diesels, right? Only the different is the different of the additive that they put into the diesel fuels, right? But the performance on the combustions probably be the same, right? For the diesel engine that's sold in Thailand, right? The performance on combustion probably the same. That's why they don't put any cetane number on the diesel fuels. Okay. When you talk about the additive, it doesn't increase the performance but it may help you have a cleaner combustion. It may help you have less wear that happen on the part of the engines. Okay, but when you want to look at the performance on the combustion of the fuel, you have to look for C10 number or octane numbers. Okay, so what is the meaning of the high C10 number for the diesel fuel? It means that fuel have a low cell ignition temperature. See, you can see the difference between the SI and the CI engine. The SI, we look for the fuel that have high cell ignition temperature. For the CI engine, we look for the fuel that have a low cell ignition temperatures, right? Because we want the fuel not to be able to self ignitions. The ignitions have to wait for the air, right, that being compressed and wait for the temperature of the air that high enough to ignite, right, the combustions. Okay, they have to wait for that, right? Not on itself. That's the reason why the fuel used need to have a low cell ignition temperatures. It have to be ignited by the temperature of the air. Okay, the fuel is injected directly into the combustion chamber at high pressures. Okay, and I put in the brackets just to remind you that less than 300 bar for the indirect injections and higher for direct injections, right? So the fuel will not mix with the air, right? The air is waiting inside the chambers, and then we inject the fuel into the chamber. So to do this, we need an injectors and a high pressure pump, right, in order to be able to deliver a high pressure fuel. Okay. The amount of the fuel now is not regulated by the throttle valve as in the SI engine. Right? The amount of the fuel is now regulated by the supply pump. Okay. It is a self-ignition engine, which is done by the compression of the air, right, in which the air, right, have the increased temperature that is required for the combustions. Okay. The typical compression ratio for this engine is what? You can see the number. Start from 12 to 24 or 15 to 23, right? Up to now, I think they do have 27, right? If I believe it's correctly, it might be for the Mazda manufacturers, okay? 27 for that, okay? So you can see that the compression ratio is much higher than the SI engine, okay? And because of this, right, they can provide a lower maximum RPM, right? In terms of the speed of the engine, right? They will run at the maximum RPM, which is lower than the maximum RPM for the SI engine, right? A good part of this CI engine is that because of the high pressure ratio that they have, they can provide a higher maximum efficiency, right? So when you compare between the SI and the CI engine, right, the CIs always have a higher maximum efficiency than the CI engine. But because of this high pressure ratio, the engine is heavier, right? High compression ratios along with the high pressure use, they result in what? The material, the part of the engine have to be stronger, right? And that make the engine go heavier. Okay. Okay, so that finished the overall outlooks of the SI and the CI engines, right? Right. We just finished the overall outlook of these two engines, right? We lay out the basic ground, how this engine work, right? The comparison between these two engines, right? How the difference of their mixtures, right? Or air fuel, right? For these two engines. Okay. Now we are going to look for a modern engines, right? A modern engines, right? It's still the SI and the CI engines, right? But it's just little bit different from the SI and CI engine on the concept of providing the fuels. Okay, this is called the stratified charge engine. Remember, charge stand for what? Charge stand for mixtures, right? Or air fuel mixtures, right? Sometimes we call it a charge. And the word stratify mean what? Mean what? Stratify mean the charge is not uniform, right? So this is the engine that we have to provide a non-uniform charge to the engine. Yeah. Let's see how good that instead of providing a homogeneous charge or a uniform charge, if we try to provide the charge in the term of non-homogeneous or non-uniform, right? How the engine responds. Okay, so the internal combustion engines where the air fuel ratio is not equal throughout the cylinder, right? We will call it a stratified fuel air mixtures, right? And this is the how we call this kind of mixture that is not equal or not uniform, not homogeneous throughout. Right. This fuel chart or this stratified air fuel air mixture consists of two layers of the fuel air mixtures. There are two layers, not one layer, one homogeneous layer or one uniform layer. There are two layers, that means it's not uniform, not homogeneous. The first layer we call is a rich mixture layer. When we call it a rich mixtures, right? Everybody know that we used to have the ratio called the stoichiometric ratio, right? The stoichiometric ratio. That ratio is about 14.7, right? It is the air fuel ratio. That means if we use 14.7 amount of the air, right? We have to use only one amount of the fuel, right? So we will have the ratio of 14.7. If we go for the air fuel ratio that less than 14.7, if it's less than 14.7, we call it a rich mixture, right? Because it's not a stoichiometric ratio, right? If it's less than 14.7, we call it a rich mixture. So for the stratified fuel charge mixtures, we have a rich mixture layer, and this mixture is provided close to the spark plug by using a small auxiliary inlet valve. Right? So we have one valve, inlet valve, that used for providing unleashed mixtures, and this valve positioned near the spark plug. Then we have another layer called a lean mixtures. So this mixture means less than 14.7. So lean mixture means greater than 14.7. Right. So a lean mixture portions, right? We provide it in the remainder of the cylinder. That means the area that not close to the spark plug or the volume of the chamber that not close to the spark plug. And we provide it through another inlet valve called the main inlet valve. Okay. And this lean mixture is the important player for the combustion, because this lean mixture layer is mainly for the combustions due to the ignitions. Okay, not the least mixture here. This lean mixture is the important player to doing the combustions for the engines. Okay. Okay. Now we have two valves, one provide rich mixture, one provide lean mixtures. Right. The way to create the lean and rich mixture, right, is by what? Okay. In order to get the lean and rich mixtures, right, we will do it through the sewer backflow, right? We use the sewer backflow or the flow of the fuel that sewer backs, right? Because by doing this, some portions of the fuels that injected, right, can sewer back to the spark plug regions, which is down here. Okay, and the sewer backflow of the mixtures, right, can be done by the shape of the piston here. Right? How we design the shape of the piston here. And this is where the fuel mixtures, right, swirl back to close to the spark plug. And this is the area where we have a rich mixture. And this is the area where we have a lean mixture here. Okay, the air is provided right here. Right. The EGR here stand for exhaust gas recovery. Okay, we will talk about this device later on the emissions, right? When we talk about emissions. Okay, so the air flow and then swirl back, the fuel injected and then swirl back. So here we have a list mixture here. Okay, so how we gonna use the shape of the piston, right, in order to swirl back the mixtures. Okay, it can be done through the wall guide that show in this picture, or the air guide that show on these pictures, or the spray guide. Okay, so let's first look at the wall guide. Right, the wall guide. This is the spark plug. This is the valve, right? Intake and the exhaust, and this is the injector. Right. So the air flow through the intake valve here, the fuel is injected here. Okay, and if the shape of the top surface of the piston look like this, the wall here will guide, right, the fuel here and also the air here, right, to swirl back, right, near the spark plug here. Okay, so this is what we call a wall guide. Okay, then look at the air guide here. For the air guide here, okay, the wall design like this here, which it look the same here, right? But for this one, we don't use the wall to guide the fuel back here. We use the air, right? The air instead that flowing down to here, we keep the air flow further here, and then it flow back. Right? Along the way that it flow back, it will draw the fuel that inject here to go back to the region near the spark plug here. Right? So this is called the air guide because we let the air to flow further down and then draw the fuel back to the spark plug here. So this is why we call it the air guide. This is the wall guide because the fuel here use the wall here to go back. Okay, to swirl back. Okay. The last one is called the spray guide. The spray guide here we locate the injector near the spark plug. So by the spray of the fuel from the injector, right, by this spray of the fuel itself, it can create the rich mixture near the spark plugs, right? It's different from these two. These two, the injector is away from the spark plug. So it have to depend on the health of the wall here and on the health of the motion of the air here. But this one, it depends on itself because the injector is located near the spark plugs here. Okay, so this is what we call the spray gun. Okay, okay. So why we use these stratified fuel air mixtures or the charge mixtures? Because this type of the engines, right, combine the best features of both spark ignitions and compressed ignition engine, right? They combine the good features of these two engines all together, right? And what are their good features, right? By first injected fuel directly into the combustion chamber during compression process. This is the good part of the CI engine, right? It inject fuel directly into the combustion chamber, and then it ignite fuel as it's mixed with air by using a spark plug to control ignition process. So this is the good part of the SI engine, right? We not rely on the temperature of the air, which can be vary from time to time. We intend to ignite it by ourselves by using the spark plug. We are the one to determine the spark or the ignitions. Okay, so this is the good part of the SI engine. Right? We control the engine power by varying the amount of the inject fuel per cycle. Right? So for this type of engine, right, our control is on the amount of the injected fuel only. Right? We let the air flow unthrottled. We let the air flow unthrottled. So that means the air is freely to flow into the engine. There is no restriction whatsoever, right? And that means what? We reduce the amount of work required by the engine. We reduce the amount of work that comes from the engine, right, in providing the pumping or drawing of the fed shaft into the cylinder, right? Remember, the engine have to draw the mixture or the air into the chamber, and this requires work, right? This requires the work. Otherwise, it won't come in, right? So if we let the air to flow freely without throttling, right, it means the amount of this pumping work can be reduced because there is no restriction due to the butterfly valve or due to the throttle valve. The air can flow freely into the chamber. We only control the amount of the injected fuels only. Okay. So this is our three combined best features of both SI and CI engine for this kind of stratified charge engine. Okay. The stratified charge engine can also avoid what? Can also avoid the SI engine required for fuel with a high anti-knock quality, right? High anti-knock quality mean what? Right? Remember, the SI engine require a high self-ignition temperature, right? So we have to provide them with a high self-ignition temperature. But since our mixture is not homogeneous, right? So that means what? Our fuel need not to be a high octane number fuels, right, as the SI engine would like to have, right? The CI engine require for the fuel with high ignition quality, right? CI engine require the fuel that can ignite itself, right? But for the stratified charge engine, they don't need to require for this fuel to have a high ignition quality because they have the spark plug. Okay, and it can replace the poor part load characteristic of the I engine. Right? If we operate the SI engine at the off-design conditions, of course, we have a poor part load performance happen. Right? This engine can replace that. And also for the CI engine, right, that will have a poor full load characteristic, a poor full load characteristic, right, for the CI engine. Okay, so this stratified charge engine can replace this characteristic of the CI engine, right? And also poor emission characteristic for both the SI and CI engine due to high peak temperatures, right? Because they go for stoichiometric ratio, right? But this engine say no to stoichiometric ratio, right? So can reduce the emissions that happen because they will not create the high peak temperatures that happen because of the stoichiometric ratio. And they also can replace the fuel deficiency for both the SI and CI engine in actual operation due to the stoichiometric fuel air ratio ignition required for these two engines. Okay, so this is what the stratified charge engine can avoid, right? They can maximize the use of the fuel, not deficiency the fuels, okay, as the SI and CI engine. Okay, so by this, since they can avoid all of this, right, the advantage is that the engine can operate it, right, can be operated unthrottled in the gate range, right, or in other words, maybe in the full range of the engine operation. The engine can run at high efficiency due to the reduction of the pumping loss, right? We don't need to provide as much work to draw the air into the chamber, right? It can tolerate a wide variety of fuel, right? They don't need to have a high self-ignitions, right? Self-ignition temperature fuel, right? They don't need to have a high ignition quality for the fuels, right? So it can use a wide variety of the fuels, right? It's good for the fuel consumption concept, right? They no need to go for stoichiometric ratio all the time. They can go for least mixture a little bit and lean mixture most. Okay, so good for fuel consumptions. And the good part is that it can provide a low exhaust emission level, both NOx and carbon monoxide, because the combustion happens mainly in the lean mixtures, right? The least mixture happen near the spark plug regions, right? The combustion of the least mixture happen only near the spark plug, but the main combustion happen in the lean mixture for the less part or the less portions of the cylinders. So low exhaust emission happen. Okay. However, if we provide too lean, okay, this is the important thing, right? Even though we have the combustion happen in the lean mixture, that means more air than fuel, then we have low exhaust emission level. But you cannot go higher and higher in the lean mixtures. There are caps or limitation on that. Because if the mixture is too lean, right, then you need to provide exhaust gas treatment, right? So the exhaust gas that come out from the engine have to be treated before, and that is expensive. Okay, you cannot provide the exhaust gas directly out from the combustion chambers if you provide a too lean mixtures. Right. This engine can be manufactured by the existing technology, right? The problem is on the nozzles, right? The problem is on the nozzle and on the shape of the top surface on the pistons, right? Because we want the fuel or the air to swirl back, right? So it's on that. But now this problem can be overcome, right? So this engine happen in the markets. Most of the engine use this. Okay. It provides a smoother and quieter operations over the entire speed and load length. Okay, so this is a good part, right? So smoother, quieter operations, right? Not like the SI, right? SI can provide smoother, but maybe not so quiet, right? Diesel, not so smooth and not so quiet. Okay, right? And this can happen, the smoother and quieter can happen over the entire speed and load length. Okay, the disadvantage of this kind of engine is what? The charge stratification can result in a lower power for the given size of the engine. So that means if you put these three engines all together and these three engines have the same size, the SI, the CI, and the stratified engines, right? If it's the same size, right, the stratified engine give you the lowest powers. Right? The engine have a higher weight than a conventional engine. Right? Compare among these three, this engine is heavier. Okay, it's complicated to manufacture, so it's costly. Okay, so the cost problem, right? But I think they overcome this, right? That's why modern engine now use this kind of stratified charge engine. Okay, the reliability is just too attractive, right? But now this is no longer the problem. But in the past, when people start to think about this, the reliability is a problem because they have rich and lean mixtures combust together. Okay, higher fuel pressure is required. Right, they have to send higher pressure than the CI engine to ensure that the fuel can swirl back. Okay, so these are the advantages. But the disadvantage that I just mentioned here, most of them now can overcome, even though not good, but part of it can now be overcome. Okay. Okay. The stratification can also be changed by the structure change in the combustion chambers, right? And on the different position of the injector and the spark plug, right? So what they said is you can change how the stratification can happen, right? By changing the combustion chamber configurations or pressing the different position of between the injector and the spark plug, right? I give you some example here for these two manufacturers, the Texaco and the MAN, okay? Through leading brand name here, okay? For Texaco, right? They put the spark plug near the injector here, right? The injector and the spark plug put close together, and the shape of the combustion chamber look like this. By using this configuration, the swirl of the fuel or the mixture will be in the clockwise directions like this. Okay, right. Clockwise direction like this. And then for the main manufacturer here, they press the injector away from the spark plug, right? And the shape of the combustion look like a cup here. Right? By doing this, the swirl of the fuel or the mixture fall into the counterclockwise directions. Right? So the direction can be changed according to the position and according to the shape of the combustion chamber. Right? So it depends on which direction that you would like to have your swirl flow to go, right? It swirl in the clockwise directions or it swirl in the counterclockwise directions. Okay, so that's the end of our first lectures. Any questions? Any questions? Any questions on the first lectures? Hello? Hello? Any sleeping? Sleeping shy? No? Hello? Hello? อ้าวเงียบอีกแล้ว Hello? 1, 2, 3, 4.
no ครับ no
No. Oh, I keep wondering why your answer is so slow. Huh? If no, you just say no. Nobody blame. Okay. Just make sure that all of you are with me. All of you are with me. Every time I ask questions, it's kind of haunting me that, hey, I'm alone or I'm with you. Okay. So if I ask, please answer. At least I'm sure that you are with me. Okay. So let's go for the second lectures. Okay. Today we will cover some part of the second lecture here. Okay. So for the second lectures, we will talk about the engine design and the operating parameters. Okay. First, we will talk about the important engine characteristics. Right. To talk about the important engine characteristics, we have to know where it comes from, right? Where all these important engine characteristics come from. Of course, it have to come from the user requirement, right? Customer is always the boss, right? So we have to look at the need of our customer, what they want, okay? And we will interpret their requirement here into our engine design considerations, right? We receive the requirement information from the user and we will interpret all that information into the engine design considerations, right? This is the engineering sentence, okay? So the user requires what? Good engine performance over the operating range, right? Because they use it at different speed. And in each speed, they prefer that the engine should provide them a good performance. Okay. Low engine fuel consumption within operating range and its cost, right? Every time that they use the engine, no matter at what speed, right? It will not spend a lot of money from them, right? The engine will not spend a lot of money from their pocket. Okay. Low engine noise and air pollutant emission within the operating range, right? The user want to be a good human being, right? Every time that they use the engine, right? Since they use the engine should not create pollution for them because they will be get affected by that pollution as well. Okay, so noise and air pollutant emissions must be low. Low engine initial cost and installations, right? The time that they buy the engine, again, they don't want to spend much, right? They want the engine to come out at the affordable price, okay? So that they can reach for or they can afford for that engine. Okay. High engine reliability, durability, and low maintenance requirement, right? They love this engine so much. They want to use this engine for a long time. This is the durability. Right? And when every time that they use the engine, they don't want to be struck because of the engine is broken. This is called reliability. And every time that they want to take care of this engine, okay, they have to run the car into the maintenance center, they want to spend less money on that maintenance cost. Okay. And the last one, user also look at how those mentioned, everything, all the requirement that we mentioned above will affect the engine availability and the operating cost. What does it mean? It means, okay, or the engineer, this is my requirement. You think that you can design or you can manufacture the engine according to my requirement or not. This is what we call the engine availability, right? They submit their requirement to the car manufacturer. The car manufacturer send all this requirement to the engineer, the design engineer. The design engineer look at it. Oh, this is good. Everything have to be good. They can invent or they can manufacture this engine or not, right? And the cost, if they can do, the cost in operating this engine will be what? Since everything is good, right? Everything is win-win. Okay, how they can make this happen, right? Or it can really happen or not. Okay, so this is how the user also think, also look at. Okay, so since we talk about the engine performance, right? What are these performance refer to? Okay, it refer to what? Maximum power or maximum torque that is available at each speed within the operating range, right? So when we talk about the engine performance, you look at maximum power, you look at maximum torque. Apart from this, you also look at the stratified length of the speed and power over the engine operations, right? You want to look at how this engine can provide the speed and provide the powers, right? What are the lengths of the speed that this engine can operate? What are the lengths of the power that this engine can give? Okay, so these two things refer to the engine performance, right? So every time that you want to compare the performance, right, you look at these two main characteristics: maximum power or torque, the certified length of speed and powers. Okay, so since we talk about the power and the speed, right, for the engine performance, let's look at the definition of the power and speed that related to the engine performance. Right. When we talk about the power, the maximum power, we have the so-called maximum rated power. Right. It's not just maximum power, it's a maximum rated power. What is this? It is the highest power that an engine is allowed to develop for a short period of operations. It means what? If you run the engines at this maximum rated power, you should not run this engine for a long period of time, right? This is what we call maximum rated power, right? The engine can provide you a maximum rated power for just a short period of time. If you try to run the engine at a longer period of time on the maximum rated power, you can damage your engine. Okay. The second one is called the normal rated power, right? Normal rated power. This is the highest power that the engine is allowed to develop or deliver in a continuous operation. So that means if you want to run the engine for a long period of time, you have to run the engine at its normal rated power, because this is the power that you can allow the engine to run in the continuous operations. Okay, so there is difference between the maximum rated power and normal rated power on the way they use on the way you use the engine. Okay. Another one is the latest speed. Right? The latest speed is the crankshaft rotational speed at which either maximum or normal rated power is developed. Right? So at the time that you have maximum rated power, what is the speed of that engine? Or at the time that the engine provides normal rated power, then what is the speed of that engine? Right? These two speeds are called rated speed. Right? So when you talk about rated speed, it refers to either the speed where the engine provides maximum rated power or the speed where the engine provides the normal rated powers. Right? That's the reason why they put the word rated before the speed, not just at speed. Okay. Okay. So that is the source where the engine performance come out. It come from the user requirements. Okay. So now we will look at first before we go to the engine design and important characteristic, right? We look at the geometry of the reciprocating engines, right? That means how we call each part or how we use each part of the reciprocating engine to do the calculations. Okay, first is the engine side, right? When we talk about the engine side, right, we talk about the volume, or we inform in the term of the volume, right? The volume give us the idea of the engine side, right? And the volume determined from the stroke and bore, okay? Stroke of the engine, the bore of the cylinder, and this volume also refer to power that the engine can deliver, right? So generally we call engine size, but in terms of design and calculation, we look at the volume and also look at stroke and bore, which lead us to the power calculations. Okay, so the piston bore is normally range from 1 centimeter, whoa, very small one, to 1 meter. You imagine, right? Very big piston with a bore of 1 meter. Right? This is normally happen in the last diesel engines. Okay, and this is important. Since heat loss and frictions are surface phenomena, not the volume. That means you can go for bigger and bigger engine, right? In which you can expect that you have less and less losses for bigger and bigger engines. Right? Why? Because of the first sentence. Heat loss and frictions are surface phenomena. That means what? Heat loss and frictions, right? The scale or the magnitude of heat loss and friction depend on the surface, not depend on the volume, right? So if you do little bit calculations on the cylinder volume, you will see that if you have an increase of the volume, the percent of the increase of the volume is higher than the percent of the increase for the surface area, right? The ratio of the volume increase is higher than the ratio of the surface increase. And this is the reason why if you go for a bigger engine, right, you can expect less losses, right, in terms of comparisons. Okay, get it for this sentence? Okay. Any question about this sentence? Any? questions? Hello? 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 1, 2, 3, 4?
no ครับไม่มีครับ
Oh, okay, everybody understand. Good. Okay, then how about the engine geometry? Because we start from volume, that means we have to refer to the engine geometry. Right? We have a crank radius. This is the first geometry, right? We represent the crank radius by a letter A. We have a connecting rod length. Everybody know where the connecting rod is, right? Everybody know where the crank is because we already mentioned in the first lecture, right? We represent this length by letter L, right? And then we can calculate the displacement volume by using these equations, right? Which are the results from knowing the cylinder bore or the piston bore, right? Or the stroke L here. Okay, so what is the stroke? What is the stroke here? The stroke is right here, right? The distance between the top center or top dead center and the bottom dead center, or in other words, is the distance that the piston can go up and down, up and down, right? So this distance, we call it a stroke here. The bore is right here, right? The diameter of the cylinder, or we can presumably is a diameter of the piston also. The connecting rod length is this, okay? And the crank radius, this is the crank, right? And this is the radius of the crank, right? This theta here represent the crank angle, right? That sometimes we represent the crank angle position by referring to what? The top center or the bottom dead centers. Okay, this is the clearance volume already mentioned, and inside here between this top dead center, the volume between top dead center and this bottom dead center is called the displacement volume or the swept volume. Okay, okay. The letter S here represent the positions of the piston, where the piston is in the cylinder, measuring from the center of the cranks. Right. So you can imagine that this is the position, this is the distance that can change. The connecting rod length cannot change. The crank radius cannot change. This angle can change. And these positions can change. Okay. Okay, the next one, again, back to our cautions, have to be cautions parameters, right? Compression ratio, geometric, not pressures, right? This compression ratio is come out from what? The maximum volume, the total volume, VD plus VC divided by the clearance volume, okay? The ratio of the cylinder bore B to the piston stroke L, the big L, right? This is the ratio of the cylinder bore and the piston stroke. We call it RBS, right? R with the subscript BS, right? B over L. We also have the ratio of the connecting rod length L to the crank radius A. We call it R, right? So R is equal to L over A. We also have the relationship between the piston stroke L and the crank radius, in which the relationship is L is equal to 2 times A. Okay, and here is the typical compression ratio that we just mentioned, right? For the SI is about 8 to 12, 13, or maximum 14. For the CI is between 12 to 24 or 15 to 23, right? Okay, this is the typical compression ratio that you use when you design the engine, right? You may go over, but if you go over, then you have to think about the material, because the mechanical loading and the thermal loading go higher when you go for higher compression ratio. right? But if you go for this number when you designing the engine, you can use conventional material that is available in the market. You don't need to bring yourself to the material laboratory and ask for all the methodologies. Hey guy, I'm going to design the engine with, let's say for the SI engine, I want to use 30 compression ratio. So you guys have to invent a good and strong material for me so that I can design the engine with compression ratio equal to 30. Okay, but if you design for typical SI or the CI engine, you can go for conventional materials. Okay, that's the reason why I have to give you the typical compression ratio right here for the SI and CI engine. Okay, for small and medium size SI engine, again, if you go for the B over L ratio within this length, 0.8 to 1.2, right? That means you don't need to go for a specialist or whatever, right? You can use conventional material, conventional equipment that is available in the market. You don't need to do for any further research in order to design your engine. Okay, so if you go for this conventional ratio, for large low speed CI engine, right, the B over L will be approximately equal to 0.5, right? This is already proved based on conventional stuff that you have or available. Okay, B over L equal to 0.5. Okay, and this table show you the typical compression ratio for different engine types, right? That you can use when you design the engine without doing any further research on the strength on the material or the heat transfer or whatever, right? Just use conventional that is available in the market. Right? For example, in here, this is the engine type. This is the length of the compression ratio, and why these are compression ratio go up to this. It's limited by all this, right? Okay, you can go further than this if you can overcome this, right? For example, for the two-stroke SI engine, right, the compression ratio go from 7.5 to 10. If you want to go beyond this, then you have to find the fuel that will not create the auto ignition problem. You have to look for a better fuel. Otherwise, you cannot go for higher than this. Okay. SI engine, right? Two valve. This is the old engine, very old one. They have one inlet valve, one intake valve, one exhaust valve. It goes from 8 to 10. This is the SI engine with 4 valves. That means they have 2 inlet valve, 2 exhaust valve. Right? They can start from 9 to 11. Not 911. Okay, they have direct injection SI engine. Right? For direct injection SI engine, you can go for higher, right, compression ratio for the conventional SI engine. Okay, and for diesel, right, they show you both indirect and direct. Right, for indirect, you see, you can have higher compression ratio than the direct injections. Okay, and if you want to go for higher than this, then you have to concern about, or you have to solve this problem, the loss of efficiency at full load, and also the component load. That means each part of the engine or each component of the engine have to be stronger. Okay, this is the thing that you have to consider, right? Or on the limited by here, this represent all the things that you have to consider if you want to design for higher compression ratio than this. But if you keep your design within this length, then you don't need to think about much. Just concentrate on your design only. Okay, don't need to think about where should I find the fuel that have high quality, where should I find a good strong material that can accompany my design. Okay. Okay, for small and medium-sized SI engines, right? The ratio R, which is the connecting rod length to the crank radius, is about 3 to 4. Okay, for large low-speed CI engine, the R ratio is about 5 to 9. Okay, for the cylinder volume, right? For the cylinder volume, right? If we want to find this volume at any crank position or crank angle theta, right? The equation show like this. Right. This is the cylinder volume at any crank angle theta. It consists of what? The constant volume, which is the clearance volume, plus the varying volume, right? Or the volume that vary according to the positions. Remember the letter S, it vary according to the position of the piston. So right here. Okay. And if we, okay, the position of the piston is shown right here, the piston position, right? If you are good in geometry, then you can easily come up with this expression S, which show you the piston position, right? I show right here the result of the expression for this position. And then if you replace this S into these equations, and then you divide this equation by the clearance volume, the result or the expression of this ratio, the volume of the cylinder at any crank position to the clearance volume will be shown like this. Okay, so like this, according to the crank positions. Okay. Okay, how about the combustion surface area? We talk about the volume, then we talk about the combustion surface area, because the heat loss and the frictions depend on the surface phenomena. So we need to know that with this amount of the volume, how much is the combustion surface area according to this amount of the volume. Okay, so the combustion surface area at any crank position theta can be represented by this expression, which is consists of what? Consists of A with the subscript CS. CS means cylinder head. Cylinder head. Okay, so ACS represent the cylinder head surface area. So that means what? The top surface here, that is part of the combustion surface chambers, so part of the combustion surface area, right? The cylinder head surface area right here. And AP, P stand for piston, right? So A subscript P stand for piston crown surface area, which is what? The top surface of the piston, which is also part of the combustion surface area. Yeah, right. For the flat top piston surface, that means if our top surface on the piston is flat, AP can be simplified from this. Pi to the ball square divided by 4, right? So the last one here, the last portion now, this is the surface area of the cylinders, right? The combustion surface area due to the cylinder itself, which vary according to the piston position right here. Okay, so now if I replace this piston position by the expression that showed previously in the previous slide, then the overall combustion surface area can be represented by this expression, a long one. Okay, long one. Okay, so with this combustion surface area, you can use this to determine the heat loss that might happen. You can use this to determine the friction loss that might happen, right? Where the power, where the volume here, you can refer to what? The powers, right? That we mentioned earlier, because volume refers to power. Okay. How about the piston motions? Right? The piston move, so the piston have the velocity. Right? The velocity of the piston usually we prefer to represent in terms of the mean piston speed. the mean piston speed is equal to 2 times the stroke, the distance that the piston can go, time with the engine speed, RPM, right? So the unit of this depend on the unit of the stroke, right? And the time depend on the speed you use, right? It can be millimeter per minute, centimeter per minute, or meter per minute, right? As long as your RPM, you use the speed of the engine in terms of the RPM, okay? So this is how we can calculate the mean piston speed according to these expressions. Okay, and this show you the typical mean piston speed. If you want to design the engine, you can use this number. And again, if you go for higher number, right, on this table, you have to do some research in your design now. Not only on the knowledge that I teach you, you have to do more research on this. But if you go according to this, again, you can use conventional material or conventional equipment, conventional OEM, original equipment manufacturer, to help you produce the engine. Okay, so this is table show you the typical mean piston speed here for varied engine, right? The racing engine, the Formula One, right? The maximum speed for the Formula One, look at the number, wow, 18,000 RPM, right? Wow, it's very fast, 18,000 RPM. So that means the mean piston speed is also high, 25 meters per second, right? For the small engine, two-stroke, the speed is also high. For the motorcycle engine, the speed is also high, 13,500 RPM, the maximum that the engine can go, right? For the SI engine, the diesel engine, and the truck diesel engines, right, the speed getting lower and lower, right? Especially for large diesel engine, right? The maximum speed is just 20 to 100, right? Medium high speed diesel engine, the maximum speed is 1200, right? And the crosshead engine, two-stroke diesel engine, 200, right? Why we call it a crosshead is a different type of the engine here. I can show you the crosshead engine. Okay, let me show you the crosshead engine, how it look like. Okay, in here, this is the crosshead engine, right? This is a typical engine, typical reciprocating engine. You can see that the crankshaft connect with the connecting rod connect with the piston. But for the crosshead, which sometimes we call it a long reciprocating engine, right? We have the cylinder here. Cylinder is up here in the opposite direction with this one. The cylinder is here. And then we have a crosshead guide, right? And the piston and the piston rod here, not directly connect with the crank, right? We have another connecting shaft here, right? Connecting rod here, another one here, right? That connect the piston and the rod, the piston rod, to the crankshaft, not like this one, right? So that's why they call this one a crosshead reciprocating engine, or sometimes they call it a long reciprocating engine because this is longer than this one. Okay, okay. So that is called the crosshead engine, and as the maximum speed reduce, the maximum mean piston speed also reduce. Okay, the mean piston speed also reduce. Okay, so we can also find the instantaneous piston speed. Before that, we talk about the mean piston speed. right? We can also find the mean, the instantaneous piston speed, right? By using this expression, the mean piston speed is equal to the differentiations of S with respect to T, the time, right? And if we divide this instantaneous piston speed by the mean piston speed, it shows you like this. The expression is shown right here, right? And if we do a plot of this ratio with the crank angle, right? Because in this expression, we have another variable, which is the crank angle or the crank position here. If we make a plot between this ratio here, it shows you like this, right? According to different R. R is the ratio of the connecting rod to the crank radius, right? So it depends on the size of your engine, okay? This R ratio gives you the picture of how big your engine is, okay? Because your engine have to occupy what? The crank and also occupy the connecting rod, okay? So it gives you like this. You can see that for the lower R, small engine, you have higher this ratio, right? And for the higher R, large engine, you have lower this ratio, the instantaneous piston speed divided by the mean piston speed. And this happened on the first half of the crank angle, right? But for the second half, everything go in opposite directions. Everything go in opposite direction. That means a small engine will experience lower ratio of the piston speed, which is good, right? And for a bigger engine, will experience a bigger or a higher ratio of the piston speed, which is good for them, right? They can withstand, right? So this just show you that, right? Even though we design for a lower R, for a higher R, right? For lower R, we have higher this ratio, higher number of this ratio for a first part of the crank angle, and then we have a lower the piston speed ratio for the second part of the crank angle, right? Which is no problem. Same as for the higher R, right? That we have a lower for higher R, that means bigger engine. We have a lower of this speed ratio, right? At the first part, and higher of this piston speed ratio for the second part. No problem. Okay. Okay, so that is about the geometry of the engines, right? I give you different ratio, right, for engine design. Right? If you would like to design engine according to the ratio that I mentioned or that I provide, then you don't need to do any further research, right? You can go straight directly, right, and produce that engine. Okay. The next one is about the important parameter. After you invent or you manufacture the engine, right? After you build up the engines, what do you have to looking for? What you have to look for? Or what do you have to look for? Okay, after you invent the engine or you build the engine. Okay, the first one, you have to find the brake torque and the brake power. When we talk about the brake, it's always mean the output, right? Okay, let me take a drink first. Okay, right? The engine will provide us not power and also the torque. The torque is important on how fast that we can move the engine or the car its initial position. Okay, so torque is important because of this. The power is how fast that we can run the car. How fast that we can run the car when the car run already. Okay, so these two have different functions. Okay, torque, we concern about torque at the beginning of the time that we start to run the car or the engine. Power is the parameter that we concern after our car is running or our engine is run. Okay. So these two things, right, normally measured by dynamometer, right, because it refers to each other. So dynamometer that show right here, we use it to measure the torque. And when we know the torque, then we can find out the powers. Okay, we will go into more detail of this dynamometer later on when we are in our last lectures, because there are many types of the parameter. But at this present time, I just want you to know that how we can calculate the torque, how we can calculate the powers, right? When we run the engine using dynamometer, the engine torque can be calculated from the force that we exerted on the dynamometer when the engine run, time with the arm of the dynamometer, which is the distance b here, right? So we connect our engine to the dynamometer and we let the engine run, right? And we want to keep the dynamometer to be able to stand still. Then we exert the force on the dynamometer, right? We keep pressing on the force until our dynamometer can stand still, right, in its initial position. And then we measure the amount of force that we exert on the dynamometer and then time with the dynamometer arm here. This gives us the amount of torque. And then when we know the torque, we can calculate the brake power delivered by the engine by measuring the speed of the engine, right, in which we measure through the crankshaft, right, the crankshaft rotational speed here, right, in terms of what? RPS. Okay, so we can determine the power delivered by the engine according to this expression, 2 pi n times torque. Okay. And if we make a plot on the torque and the power for the different engine speed, this is what we get. Right? We have two curves. In these two curves, you can see that we always get the maximum torque at the lower speed than the speed that we get the maximum powers. This is what we always get, right? The maximum torque occur first, and then the maximum power occur later, right? So that's the reason why when we start to run the car, torque is more important, because we want the torque to push the engine to keep walking, start walking, not keep walking, start walking. Okay, so we want the torque as high as possible, right, at the lowest possible for the engine speed, so that our car can have a quick start, right, quick start of takeoff. Okay, and when it runs, right, we want it to run as much as they can, right, or at the maximum speed as high as they can. In which, on that condition, we have to look for maximum powers. Okay, so maximum power come after, maximum torque come first. Okay, so maximum torque is normally at the low speed and increase sharply. Right, this is the characteristic of the engine that we would like to happen. We want it to increase quickly, right? While the maximum power is at higher speed and increase slowly, because at the beginning we don't want to have a maximum power. We look for a maximum torque. Okay. The second parameter is called the indicated work per cycle. Indicated work. Okay. If you still remember in thermodynamics, we used to talk about this before, the indicated work. Okay. Right. The indicated work can be calculated from these expressions. Most of you should be familiar with, right, in thermodynamics. Right. C stands for cycles, because when we talk about the indicated work, we don't talk about the process. We talk about the cycle. So C stands for cycle. I stands for indicated work. Right. Since it talk about the cycle, our integrations, our integrations have to be what? The cyclic integration. Don't forget about the circle here on the integration side. It represents a cyclic integration. It is a cyclic integration of what? The pressure times the differential volume here, right? This is how we can get the indicated work if we want to do by hand or do the calculations, right? That means what? That means we have to find the pressure distribution that happened in the engine, right? And we have to find the change of the volume. Time these two together, get all every piece of this multiplication, sum it all together until the cycle finish. Then we can get the indicated work shown right here. And this is for one cylinders. Okay, so I show you two diagrams here, right? The first one is for the two-stroke. This diagram is the pressure and the volume diagram. The first one is the two-stroke engine. The second one is the four-stroke engine. Right? In thermodynamics, right, the two-stroke PV diagram is more familiar to you. Right? Why? For the four-stroke, right, four-stroke PV diagram, I think most of you probably haven't seen it, not familiar with, right? But for two-stroke, familiar with. Right? And for this two-stroke, if you want to apply these equations on this two-stroke PV diagram, it's really straightforward, or you can apply it directly, right? Because the cyclic integration of P times dV here represent what? The enclosed area of these cycles, right? The enclosed area here, right? And if you remember, we just mentioned earlier, the exhaust valve open and the inlet valve open at what? During expansion here, right? During expansion stroke here, right? Where the exhaust valve open, that inlet valve open here. Okay, so the indicated work can be calculated by measuring the enclosed area here. Okay, but for the four-stroke cycles, right, there is some ambiguity, right? That means there are some confusing here are introduced here, because when you look at this PV diagram here, you can come up with two definitions of the indicated work or the indicated output that is commonly used when you look at this one. The first one, we call it the gross indicated work per cycle. Gross indicated work per cycle, we use the letter like this. C stands for cycle, I stand for indicated, and G gross, right? So for the gross indicated work per cycle, it means what? it means the total work delivered to the piston over compressions and expansion stroke only. So where is the compression and expansion stroke? Compression start right here and go and go and go. So it end of compression here and then start of expansions and finish here, right? Finish right here. So that means the area that represent the gross indicated work per cycle, right? That cover compression and expansion stroke gonna be the area that the combination of the yellow area here and the blue area here, or the area A and the area C, right? This area represent the gross indicated work per cycle. Okay. The second definition will be the net indicated work per cycle. Right? When we talk about the net, you have to think about something that we get after we pay for. Right? But for the gross is you have to think about what? Something that we get without consider anything that we have to pay for. This is what we mean, the gross. Okay? But net, when it comes into your mind, you think about give and take, right? Give and take. But gross, you have no give, you take only. Okay. So the second definition called net indicated work per cycle, right? Again, C stands for cycle, I stand for indicated, and N stand for net, right? It is the network delivered to the piston over the entire 4-stroke cycle, right? For the gross, we only concern compression and expansions. For the net, we concern both intake, compress, expand, and exhaust, right? So that means the net indicated work represent the area of what? The area of the pink color here, which show by the letter A, right? Minus the area that show by the soft green color here, which represent by the letter B, okay? So this is called the net indicated work per cycle, right? That means what? We have the work that is positive, which is shown in the pink color. This is the positive work. And we have the negative work, right? The positive work is pink color. The negative work represented by the soft green color here, right? Why this work become negative? See, because things happen, right, below atmospheric pressures. We have to expel something which we call the exhaust gas, right? So we have to provide work to expel or to release the exhaust gas. We also have to provide work in order to what? To draw the air into our engine. This is the work that the engine have to give, right, before it create the positive work here. So they have to pay first and get the result back, right? So in overall will be the combination of these two, in which one is positive, another one is negative here. Okay, so that's why the net indicated work per cycle is the area A minus area B. Okay, how about the area B plus the area C here? Right, the area B plus the area C here. The area B plus the area C refer to the work transfer between gases. That means what? The exhaust and the intakes, right? In the piston and the cylinder during the intake and the exhaust work. This is what we call the pumping work. Remember the pumping work. Pumping in, right, for the intake, pumping out for the exhaust. Right. So in overall, we call it the pumping work. And can be calculated from what? The gross indicated work per cycle minus the net indicated work per cycle. Right. The difference between these two represent the amount of the pumping work, the work that we need to pump in and pump out of the gas. Okay. So for naturally aspirated engine, the engine that draw the air by itself, the pumping work here is the work that transfer to the gas in the cylinder, right? When we say the work that is transferred to the gas, it means we have to give this work to the gas, give them the money, right? So that you should come in, you welcome to come in, and you welcome to go out, right? We give them, right? For that they can come in and they can go out, okay? We have to give this work because the pressure during the intake stroke is lower than the pressure during the exhaust stroke, right? Remember at the very beginning of the lectures, right? The exhaust pressure is higher than the intake pressures, right? So that for the intake to go in, we have to give them work, okay? How about, so this become a negative work, right? This pumping work become a negative work because we have to give the work to the gas. For highly load turbocharged engine, now we have a turbocharger to help the incoming gas or the incoming air to flow in, right? The pumping work is transfer from, not to, from cylinder gases to piston. Now we get the work out from the gas. We get the pumping work out from the gas, not like the previous one that we have to give the work to the gas. Now with the turbocharger equipped to the engine, this pumping work become positive for us. Why? Because now the pressure during intake is higher than the exhaust, right? The pressure during intake is higher because it gets the pressure from the turbochargers. So it has more power, right? So it can flow in easily. The engine don't need to give me the power, don't need to give me the money for me to get the ticket and go in, right? I can go in by myself because I have the turbocharger to help me, right? So the pumping work become the positive. That means the engine get the pumping work out because of the turbocharger. And that is the reason why engine, when equipped with the turbocharger, it gives you a higher amount of work than the engine without turbocharger. That advantage come out from the pumping work that used to be given, but now, right, this pumping work become our helper. It give back to the engine, right? Because they don't need to give this to the gas due to the turbochargers, okay? So that's the reason why engine with turbocharger can provide higher work than the engine without turbochargers, okay? Okay, so the indicated power per cycle, or in short, we call it the power per cycle, right? Can be either gross and net, as we mentioned, right? So the power, if we want to determine the powers, before that we talk about the work. Now we talk about the powers, right? So the power now can be determined from what? From the indicated work per cycle. This one can be either gross or net, right? If it come out from gross work, then this is the gross power. If it come for net work, then this is the net power, right? This work have to time with the engine speed, right, in the unit of RPS, and divided by N sub R. This N sub R is what? Is the number of crank revolutions for each power stroke per cycle. Remember, we have 4 stroke, we have 2 stroke, right? So that means for the 4 stroke, every 2 round of the crankshaft rotation, we get just 1 power. So this NR have to be equal to 2 for 4 stroke. And for 2 stroke, every round of the crankshaft rotation, we have powers, right? So this NR equal to 1 for the 2 stroke here, right? So this is the expression that we can convert from work to powers, right? For the indicated powers. Okay. So this I show you again for the 4-stroke SI engine that equipped with supercharger or turbocharger. The difference is on the lower portion here, right? This one is for naturally aspirated engine, right? You can see that the lower portions is always less than the atmospheric pressure, while for this graph, the lower portion is always higher than atmospheric pressure, right? So that means what? The intake is higher than the exhaust. And for this one, the exhaust is higher than the intakes, right? So the net indicated works, because this is IN, N net, I indicated, C for cycle. The net indicated work for cycle or per cycle for the turbocharged or the supercharged engine will be what? Area A plus area B here, because both areas are positive. Where for the naturally aspirated SI engine, the net indicated work per cycle will be area A minus area B, because this area B is a negative work. Okay, the next one is the mechanical efficiency. The mechanical efficiency, right? When we talk about the mechanical efficiency, we have to talk about the power, right? Again, we have the gross indicated power. But this gross indicated power, it measures from what we get outside the engine, right? Previously, this gross indicated power, we receive it from what happened inside the engine. That's the reason why we have to talk about P and V diagram. That means we get it directly. We want to directly find out what is the gross indicated work or the net indicated work, right? But in here, I just show you another way that we can find the gross indicated power, right? But this time, we find it from what is going out from the engine, right? And there are 2 power going out from the engine. One is the power that we get, we call it the brake power, right? And remember, we get this brake power from what? From the dynamometer when we test the engine. Plus another power that also come out from the engine, but we cannot use it, right? This is called friction power. So sum of these 2 equal to the gross indicated power. And this gross indicated power is equal to what? The indicated work times the engine speed divided by the number of crank revolutions. Okay, where the indicated work, we get it from the integration, cyclic integration of the pressure times dV, right? So we can either find it from the left with it inside the engine, or from the right with it outside from the engine. Both are the same. Okay, so in terms of mechanical efficiency, right, by definition of the efficiency is always something that we use or we get divided something that we have to pay for, right? So the mechanical efficiency will be what? The brake power divided by the gross indicated powers, right? Or in other words, it can be 1 minus the friction power divided by the gross indicated power here, right? So this mechanical efficiency depend on what? How much we can get the power out from the engine, which depend on the throttle positions. How much we let the air to flow in depend also on how good we design the engines and depend on how we operate the engine, which is the engine speed here, right? So if we widely open the full throttle, we let the air to flow freely inside the engine, then the mechanical efficiency can go up to 90%, right? At the speed below 1800 to 2400 RPM, right? And it can be down to 75% if we run the engine at the maximum rated speed. This is the length of the mechanical efficiency, 90 to 35%, right? And if we more and more engine throttle, right? That means if we throttle the engine, or in other words, we let less and less amount of air to flow into the engine, the mechanical efficiency will go down and down, right? And it will be zero at the idle speed. Okay, so the question is why this mechanical efficiency is zero at the idle speed? Anyone can give me the answers why the mechanical efficiency becomes zero at the idle speed? Hello, 1, 2, 3, 4. Hello, hello, hello. Oh, ปวดหัว Hello, anyone hear me? Hello world ได้ยินไหม
ได้ยินครับ
โอ้ยไม่ตอบเลยเนี่ยตอบไม่ได้ก็บอกว่า no I cannot แค่นั้นแหละฮะมันจะได้ไม่ต้องถามหลายทีทำไมมันถึงเป็นศูนย์ why it becomes zero sir I don't know just say this นะ if you really don't know
ไม่ทราบครับอาจารย์
แค่นั้นแหละนะอาจารย์จะได้ไปต่อไงนะเพราะอย่างน้อยก็รู้ว่ามีคนฟังอยู่นะครับโอเคมันเป็นศูนย์ it becomes zero because if you look at the definitions, right, when you run the engine at idle speed, does the engine move? No, the engine do not move, right? The car do not move. That means what? You don't have power output come out, or it come out but you don't use it. That means what? Zero. So PB is zero, and that's the reason why mechanical efficiency is zero. As long as you don't use that power for your own sake, right, you will consider that mechanical efficiency is zero. So it's zero at the idle speed. I think everybody understand about the idle speed. ภาษาไทยเรียกว่ารอบเดินเบารอบเดินเบานะครับก็คือ start engine แล้วก็ run engine อยู่ตรงนั้นนะครับไม่ได้เคลื่อนที่นะครับ this is what we call idle speed. Okay, the next one is called the load power. The load power. This is more concerned power in terms of car manufacturers. Right? The load power, because they will look at the engine with the car all together. Right? Before that, we just only look at the engines. Now they look at the engine with the car altogether, right? So they consider about load powers, right? It is the power that overcome the rolling resistance. Right? This rolling resistance come out from the friction of tires and the aerodynamic drag of the vehicles. Right? This load power is the reference point for testing the automotive engines. Okay, that's what I mentioned, that most car manufacturer, right? They concern about the load power because they look at the engine and the car altogether, right? So this load power come out from these expressions, which consists of what? Right? The power that overcome the rolling resistance due to the mass of the engine itself or mass of the car itself, right? Plus the power that required to run the car at one certain speed here, right? So the power to overcome the rolling resistance because of the mass of the car, MV here, plus the power that to overcome the resistance force when, or the drag force or the aerodynamic force when the engine is run or the car is run at this speed of the car. This is the speed of the car, not the speed of the engines. Okay, that difference, right? S sub V means the speed of the car. Okay, so C sub R here stand for the rolling resistance coefficient, which is in the length of 0.012 to 0.015. MV is the mass of the vehicle or the mass of the car, right? For the passenger car, it refers to the curved mass plus the passenger load of 68 kilograms. Okay, so this mass of the vehicle is not only the mass of the car itself, but also includes the mass of the passenger that sit inside the car, and that passenger weight is 68 kilograms. Okay, CD show right here is the drag coefficient for the car. The CD usually designed in between 0.3 to 0.5. Okay, I talk about the typical car. Okay, and low A here represent the ambient air density. A sub V represent the frontal area of the vehicle. S sub V is the vehicle speed or the car speed in terms of meter per second. Okay, and G represent the acceleration due to gravity. Okay, G right here. Okay, and if we use the standard ambient air density and the standard acceleration due to the gravity, which is equal to about 9.81, something like this, then this expression can be expressed in this formula, right? Where the unit for each parameter show right here, right? And the result of the power is shown in terms of the kilowatt here. So this is the expression to calculate for the load powers. Okay, and this picture show you how the flow resistance occur. Right, you have the shape of the car. For different shape, you have different flow that happen to the car. Right, the first one is a very old car. We call it a square shaped car. Right, you can see that you get the eddy flow or the flow separation behind the car. Right, this create the resistance to the car that the car have to overcome. Right, for a streamlined shape of the car, you can see that the flow is smooth. Right, it flow from the front and leave behind the back of the car smoothly. Right, so the streamlining the car means shaping the car such that the air flows smooth over and around it, rather than forming the eddy that will hold back the car and the powers. Right. So this is what happens if you have different shape of the car. And so where the drag happen in the car, it show right here, right? The side of the car, normally there is no drag, no significant drag happen, right? Most of the drag that resists the car come out from the wheel, come out from the side mirror a little bit, and you can see mostly come out from the back of the car. This is where the drag happen and the car have to overcome when it run. Okay. All right. Now, if we want to delay the force separation, that is the original source of the drag, right? If we have the force separation, then we have the drag happen here. If we want to delay the force separation, that means what? When we talk about the delay of the force separation, it doesn't mean that we don't let the force separation to happen. It means we allow it to happen. But if it happens, please happen outside the region of the car, not within the region of the car like this. Right? We want it to happen outside here. Okay, that is what we mean. Delay the force separation. What we use is we use the vortex generator, right? Vortex generator, because if we can create the vortex flow, right, to the flow that pass to the car, the vortex system that happen in the wake of the car can help delay the force separation. This is the key point, right? We want to have the flow that go like vortex or the vortex flow, right? Because this vortex can help delay the force separation or bring the flow to go separately or happen later on after it leaves the car. Okay, and this shows you the typical device that we call the vortex generator. It may be on the roof of the car here or at the back of the car on the roof, but it can also be installed at the side of the car here. This will help create the vortex flow when the car running, right? And it will delay the force separations. Okay, this shows you the difference drag coefficients for various shape of the body, right? You have a flat plate here, you have a high CD here, right? For the hemisphere that encounter directly with the flow, the CD is also high, but you have a hemisphere that is not encounter directly with the flow, then you have CD low here. And especially for the airfoil shape here, right? Airfoil shape here, you can see the airfoil shape here that look like this for most of the aircraft wing or the airplane wing, right? The airplane wing will have a shape that look like the airfoil shape here, right? And you can see that the CD is very, very low here, right? And this is the generation of the car, right? We used to have this type of the car that our CD is very high here, right? And then we change the shape of the car in order to get a lower CD, right? This is the pickup, a little bit that we can do on the chain of the car, right? And then this is the modern one, right? That mostly you see the car that look like this, where the CD is about this or a little bit less than this. Okay, the next one is called the mean effective pressures, MEP, mean effective pressures. Okay, this will be the last topic we will talk about in today's. Okay, we will finish our lecture after we finish this. Okay, the mean effective pressure, MBP, I put in the bracket. This is a standardized way of stating torque relative to the displacement. Okay, what is the meaning of torque relative to the displacement? Right. This is the way that we can compare for different side of the engine that provide us different torque. Right? So with this MEP, we can determine which one is the best. Right? Otherwise, we may talk about, oh, this engine give us bigger torque because of the size is bigger. Right? This one give us a smaller torque because it's a small size. So which one is the best? We don't know. Which one is better than another one? We don't know. Right? So we use this parameter, the mean effective pressure, to be able to compare, right, when we have the ratio of the torque relative to the displacement here. Right? So mean effective pressure come out from what? Power. Remember, we have two power initially, right? When that we talked earlier, one is the indicated power, another one is the brake power, right? So since MEP calculated from power, and power can be either indicated power or the brake power. That means MEP can also be either indicated mean effective pressure or brake mean effective pressure, depend on what power that we put in. Okay, so power times the number of crank revolution divided by the displacement volume and divided also by the engine speed. All of this will give you the mean effective pressures, right? And the unit of the mean effective pressure can be kilopascal here, right? And if we use the unit in terms of kilopascal, our volume can be kilowatt, right? While our power is in kilowatt. Our volume, right? Normally, right, when we talk about the displacement volume of the engine, right? If you go back to the picture that I showed you in the first lecture, right? When we talk about the engine size, right? People prefer to talk about the engine size in terms of what? Liter, right? Liter, right? Liter can be easily referred to decimeter also, right? Or in refer to meter as well, right? If we refer to the displacement volume, if we refer the displacement volume to decimeter here, right? Then we have to time with 10 to the power 3 up here in order to keep the unit kilopascal right here. And the number of speed is RPS, right? And for power, right, if it is a brake power, right, then we can convert this power into torque. Remember, right? For the brake power, we can use torque to come up with the powers, right? So now we change the power into torque, right? That means the speed dismissed, right? So another expression of MEP in terms of torque will be like this, right? Leave only just 6.28, which come out from what? 2 times pi. 2 times pi equal to 6.2x, okay? So we have two expressions for the mean effective pressure, right? Either in terms of power, either in terms of torque, okay? And for naturally aspirated, when you design the engine, right, with conventional material, with conventional equipment, device that you have, the maximum brake mean effective pressure, brake mean effective pressure, BMEP stand for brake mean effective pressure. The maximum one will be around 850 to 1050 kilopascal at the maximum torque, which is 3000 RPM. Okay, and if you design at the maximum rated speed, rated power, the brake mean effective pressure will reduce to 10 to 15% lower, okay, from the above, okay, because this is the value that you design at the maximum torque, and this is the value when you design at the maximum rated powers. Okay. For the turbocharged SI engine, the number for the maximum brake mean effective pressure will be around 1250 to 700 kPa, right? And at maximum rated power, the brake mean effective pressure will be about 900 to 1400 kPa. Right? For naturally aspirated 4-stroke CI engine, the maximum brake mean effective pressure will be about 700 to 900 kPa, and at maximum rated power is going to be about 700 kPa. Right? And for turbocharged 4-stroke CI engine, okay, the maximum brake mean effective pressure will go higher, right? You can go higher to 1000 to 1200 kPa compared with the natural aspirated 4-stroke here. Okay. For turbocharged with the aftercool mean you compress the air and then you let the air flow through the intercooler to reduce the temperature. If you remember, then your maximum brake mean effective pressure will be about 1000 to 1400, right? And at maximum rated power, right, the brake mean effective power will be about 850 to 950 kilopascals. Okay, lower. The 2-stroke CI engine, right? All above here, we talk about 4-stroke CI engine, right? So I mentioned right here, for the 2-stroke CI engine, right? You can use approximately the same as the 4-stroke SI engine here, right? Because it will have a comparable performance to the 4-stroke SI engine. Comparable performance, it means the same brake, the BMEP that I just mentioned for the 4-stroke CI engine. Right. For example, for large low-speed 2-stroke CI engine, the BMEP could go about 1600 kPa, compared with the turbocharged SI engine, in which maximum BMEP is about 1250 to 1700 kPa, right? About the same within the length of the SI engine, same one. Okay, this table show you the typical mean effective pressure for various engines, right? Then you can use this number to do your engine design, right? Okay, this is the maximum one up to, right? So for motorcycle, you can use the number for the effective mean the mean effective pressure to go up to 12. That means what? You can use 10, 8, 9, up to 12. If you want to go higher than 12, again, you have to do a little bit research on that. Okay. Racing engine, 16. Okay. And for other car, other type of the engines, right? SI, right? Turbocharged, without turbocharged, right? For turbocharged, you can go higher. Right? For the diesels with turbocharged, right? For the truck diesel large engine, you can go up to 22. Right? For high speed, you can go up to 30. Right? But for medium speed, then you have to go lower. And again, for the crossheads, you have 15. That's your maximum. Okay, so I think I will better stop here. Huh? Or we should finish this example. Huh? Let's see how many pages. Okay, 2 pages only. Yes. Okay, let's finish it. Okay, examples. Okay, this is
Could you do it next time?
It's only 2 slides. You exhausted?
Yeah.
I see. Okay, so we will do this example next time. It is a design examples. Okay, so I will stop right here up on your request. Okay, no problem. Okay, you feel free to ask me if I a little bit go over the time. Don't worry. Don't hesitate to tell me. Okay, I will do according to your views as long as the time is already finished. Okay. Okay, so we will stop right here. Any questions? Any questions? Any questions for these lectures?
ปกติอาจารย์มีเวลาเบรกไหมอะคะในคลาส
จริงๆเนี่ยถ้าสอนปกติจะมีเบรกนะแต่สอนออนไลน์มันก็ไปได้เรื่อยๆหรือคุณจะให้อาจารย์เบรกเหรออยากเบรกเหรอ
นิดนึงก็ดีค่ะ
เหรอไม่ไหวใช่ไหมนะนึกว่าฟังแบบชิลๆสบายๆไปเรื่อยๆ โอเคไม่เป็นไรอย่างนั้นเดี๋ยวครั้งหน้าอาจารย์จะมีเบรกให้ก็แล้วกันนะสักประมาณ10 นาทีนะนึกว่าออนไลน์มันสบายนี่นั่งนอนก็ฟังได้นอนบนโซฟาก็นั่งฟังได้ไม่เหมือนนั่งในชั้นเรียนใช่ไหมถ้าชั้นเรียนมันต้องนั่งเก้าอี้มันก็อาจจะมีเบื่อบ้างแต่อันนี้ก็นั่งฟังไปเรื่อยๆนะเหมือนฟังดีเจนะคิดว่าฟังดีเจรายการวิทยุ นะโอเคไม่เป็นไรงั้นเดี๋ยวครั้งหน้าก็อาจจะมีเบรกให้สัก10 นาทีก็แล้วกันนะโอเคตามนี้โอเค any questions
ไม่มีครับ
ไม่มีนะโอเค so I will finish this lectures today okay so see you next week everybody okay bye bye
สวัสดีครับ
สวัสดีครับ
ครับ
สวัสดีครับ
ขอบคุณครับ
Yeah.
ขอบคุณครับ